So, how many of you have heard of logarithms before? Yay, a couple of us. The rest of us are like, what in the world? All right, so here's what logarithms do. Logarithms allow us to solve for exponents that are unknown. Okay, so in other words, maybe you have something like 3 to the x equals 15. Okay, we don't know how to get x by itself, right? But what logarithms do is they let us rewrite things so that we can solve for that exponent value. Another way to write, they're actually the inverse of exponentials. Excuse me. All right, so they look a little funny. This is how we write logs, all right? We have a little teeny number here that's written as a subscript. That's called a base. So we read this as log base b of a. And logs always, and I'll say this 1.5 million times, logs always equal exponents. That's what we always set them equal to. So it helps you remember because the order to switch them around kind of gets confusing. All right, so if this is what the log looks like, log base b of a equals x, then an equivalent equation here would be, look, base of b, log equals exponent equals a. These are the same, these are the exact same thing, they're just writing them a different way. Okay, so let me show you with an example exactly. Let me show you an example. If I know that, but let me say this while I'm here. This is what we call logarithmic form. This is what we call exponential form. And so to be good with logs, you have to be able to fluidly go from one form to the other. All right, let me see. Do you all agree with the following statement? Yeah. We agree that's true? How might you write that in logarithmic form? Yeah. Log, what's the base? Of. Logs always equal exponents. So it's 9 equals 2. Okay, that's just changing forms right now. We're going to do a lot more with it. But right now, okay, logs equal exponents. Logs equal exponents. How about, Not today. What would the exponential form be? 5. Do you see how we're changing forms here? Going from everybody can do that. Let me give you a little bit tougher one. It's 36. Come on. 1/2. And Cameron, I think this is what you were getting at. An exponent of 1/2 is the same thing as what? A square root. Okay. So is that true? Is the square root of 36 6? Yes. Dumb pens get on my nerves. What? You need me to go back? Tell me what that might equal. Not what it might equal, but what does it equal? So run me through your thought process. What are you doing? 2. Well, remember it's going to equal power. So 2, what would go here to make this equal 8? 3. Do you all see what we did there? You're kind of thinking through exponential form in your mind. How about 1? Why? 7 to the first power is 7. God, you got it too quick. Nobody ever gets that one first. All right, 0. You're right. Because anything to the 0th power is 1. Huh? So let me give you a couple properties of logs. And really these make sense. You've just derived several of them on your own. The first one, these are what we'll call basic properties because we'll talk about some more complex properties tomorrow. It does not matter what the base is on the log as long as it's not 0. If this number is 1, this is going to equal 0 every time because the only way to get 1, yeah, exactly, raised to the 0 power. The second property, if the bases are the same, if the base is the same as the A, what does it equal? 1. Because B to the first power is B. Here's one that you may not, well, you probably won't know. If the bases are the same, and this B has an exponent on it, let's say it has an exponent of X. This simplifies down. Instead of 1, it's just X. So if I asked you, what is the log base 8 of 8 to the 5th? It would just be 5. And probably the most confusing one, if you have some base and you raise it to this power of a log with the same base, it's just X. An example? 12 raised to the log base 12 of 15. It would be 15. It is. They're very similar. Log button on your calculator. That log button does not do just any old log, though. Because we have what is called a common log. You know, math is always saying there's an imaginary something somewhere if you don't see it written. If there's no exponent, there's an imaginary what? 1 exponent. If there's no coefficient, then it's a 1. If there's no number written right here for the root, then it's a 2, right? There's always something there if there's not anything written. The same is true with logs. If you see a log written and you don't see a base, that indicates the common log, and it's a base of 10. And your calculator, if you push the log button on your calculator, that's a base of 10. Okay, so don't think if I asked you what's log base 2 of 8, you're not going to be able to put that in your calculator just yet until I show you how to do it, because it's just going to do base 10. You don't, or you do? That change of base form. So tell me this. What would be the log of 100? 10? The base is 10. What would the exponent need to be to get 100? 10 to the 10th power is big, 2. Think exponents, not multiply, okay? How about you have to really think about that one. It would. Good job, Silas. Why is it 1/2? Log, that's exactly right. This is the same thing as 10 to the 1/2. And since now these bases are the same, that property tells us if those bases are the same, it just leaves us with whatever this exponent is. Does that make sense? Does it make dollars?
Because sense.
If it makes so much sense, then does it make dollars? I know. Before I do natural logs, let me just show you this. Let me show you how we can use this in a basic form. If I had the log base 2 of x equals 5, and I said solve that for x, what would you do? You absolutely could. You could change the form. Here's what I'm going to tell you whenever you're working with logs or exponents. If at any point you get stuck and you don't know where to go from there, always change the form. Because more than likely the answer of what you need to do is going to pop out at you when you change forms. So try to change forms when you get stuck. And now it's easy to see what x equals, right? X is 2 to the 5th, which is 2, 4, 8, 16, 32. Everybody okay? I got one more type of log to show you if everybody's okay. So we did log with any base, we did common log, and now we're going to do natural log. And that's it. We're not going to do graphs today. It's too much in a day assuming that you did not get logs in algebra 2. Everybody got that? All right. All the same properties of logs still apply to natural logs. There's no specific base for those. Those are general type properties. So all those same properties will apply here. But what a natural log is a log whose base is e. Remember that e we talked about yesterday? Okay, so that's a natural log. And instead of writing log base e, what we do is we write L in, and that tells us that it's natural log. Okay, that's not a 1, that's an L. It's not an I. But you have to keep in mind that it's got a base of E. Okay, especially when you're simplifying and stuff. Some of y'all look so bored right now. I'm almost done, I promise I am. What if I asked you what this equaled? What's going on? Why? Why can you just take the exponent? This is E and the base is E. They're the same thing, that same property. You could write this like this, right? There is a natural log button on your calculator, okay? It is right under log, okay? So keep in mind, this log is doing log base 10. So if we did that log of 100 like we did a minute ago, and it's 2. This log is the natural log, so that's log base e. So if we did the natural log of e, what did I say to the 5th? It'd be 5. Okay. So it will do those for you, but whenever you start mixing your bases up, it's not going to do those for you. Okay. All right, tell me what you think about logs, because I've never taught it that fast.
Let's get this homework. I might finish it now.